All right. Welcome, everyone. Thanks for attending this webinar on advanced materials for modulation. It's the second in a series that Luceda's been running, and I'm delighted today to invite Dr. Steve Allison from OpenLight. He's going to be sharing a little bit about their platform, their technology, and hopefully there'll be some interesting questions at the end. Um, I will briefly present Luceda. I'll introduce us and describe some of the work we're doing in this area. And I'll hand over to Steve and he can get into the details that I know everyone is here for. I'm also joined by Kevin McCumber from Spark Photonics. They're our partner and redistributor in North America, and he'll be moderating the Q&A at the end. As you may have noticed, the session is recorded and it will be shared with you afterwards as well. So very briefly, I don't want to take too much time away from Steve, but if you're not familiar, Luceda is an EDA software company headquartered in Belgium, but with partners and offices around the world. We're founded more than 10 years ago now, and in that time, we've been a photonic EDA company supporting hundreds or thousands of customers through tape outs all around the world. And our mission is really to bring the same kind of first time right design that people experience in electronics and try and replicate that in the photonics market. We have a range of platform of products as well as services. These cover everything from design and simulation, so that's IPKISS as our core product, but also we have other products as well, such as our line of data analytics tools and verification tools, such as our DRC engine. We also support many design kits, assembly kits, test kits, of which OpenLight on the tower process is one of them. Um, Speaking of that, we work closely with foundry partners on PDK development, whether that's test site development, model building, characterization. This is something we're heavily involved with and consider ourselves experienced with. So if this is interesting to you, please reach out to us or to OpenLight and let us know what your questions are. Um, Along the same line, something I wanted to briefly touch on is we have a line of tools to do with big data analysis, specifically for photonics. This is something that appeals to foundries, but also to large companies that struggle to manage their data and really draw a lot of insights from this. So this is everything from drawing your wafer scale data all the way up to extracting the key parameters and figures of merit and using that to build statistical models. Finally, once you have those models, we also do a lot of work in yield prediction, enhancement, and analysis. On the software side, we have tools that can run circuit scale simulations on corner analysis, Monte Carlo, and layout-aware variability. This provides a powerful platform to compare different architectures before you tape out to try and maximize yield, using whatever data is available, whether that's foundry data, measurement data, or even synthetic data. There's also a lot of options within this. As I've kind of put on this slide, we can look at things like variability in wafer thickness, sidewall angles, roughness, dimensions, temperature. So it's really is quite a comprehensive set of solutions. And then finally, all of this is supported by a large service offering that we have, everything from test key design to building these libraries and models on behalf of foundries and customers all around the world. The final slide from on me at least is we also have a link for Cadence. This is quite timely because I know that OpenLight have recently announced their Cadence PDK. So this is how we're targeting co-design and co-simulation workflows. And you can find more details about this on our website. I'd also like to introduce Spark Photonics. As I mentioned, we're joined today by Kevin McCumber. Spark are our partners in North America, so they represent us and handle sales and support. But they're also a company separate to Luceda, and in their own right, they offer technical services, software, and pick kits. If you have any questions for them or for me, feel free to reach out in the chat. We'll moderate the questions at the end, or you can reach out via email afterwards. And then finally, I'd like to hand over to Steve. I've known Steve for quite a few years now. He's hugely experienced in the photonic market, and we're really lucky to have him today. I know he's a very busy man. He's currently the head of business development at OpenLight, or senior head of business development at OpenLight, where he's been for about 4 years, I believe. And then before that, he worked at Juniper as well as Ericsson. So he's really an industry veteran. But I'll leave it to him to introduce himself and what OpenLight are doing. Steve, thanks. The floor is yours.
Thanks, Matt. Appreciate the introduction. Let me just get my screen share up. That's going through for everyone.
Yep,
Thank
looks
you.
good.
Okay. All right. So thank you very much, everyone. And I really appreciate the opportunity from Luceda and Spark to talk to you today about some of the work that we and some other people have been doing on materials for modulation. And specifically, what I'm going to cover mostly today is heterogeneous integration of 3,5, specifically indium phosphide, on silicon, and how that can be solve some of the pinch points and problems that as the scale of AI starts to increase, is driving the industry towards today from there as well. So, so what's the problem statement from here as well? I mean, I think you probably need to have been living under a rock for the last couple of years to realize the impact that AI has had on the optical industry. As Matt kindly reminded me, I've been doing this for a couple of years now, and even since the year 2000, the interest in optics from all sections of the community, financial, technical, is unprecedented, and that's because AI is driving huge, unprecedented, and ever increasing growth in the needs for compute power, and then that drives the need for connectivity between there as well. Um, and connectivity used to be, the least part of everyone's problems, but now it's become identified as one of the bottlenecks, primarily because it hasn't kept up with the growth in computing power from there as well. And these trends are not slowing down any at all. We use numbers from a couple of analysts. We get quarterly updates, and every quarter the numbers go up by about 10, 15, 20%. And what is being deployed now is a fraction of what's going to be coming down the pipe from there as well. So we have a nice problem to solve. We have a huge demand for our solutions from here as well. Bandwidth is increasing. The amount of just sheer physical number of lasers, amplifiers, modulators, detectors that is going to be required keeps increasing. The speed increases year on year. Um, and the way that the optical industry has typically built things in the past, which is by taking piece parts and putting them together into pluggable transceivers, really is starting to break from there as well. Now, silicon photonics is obviously the key technology to start with from building some and solving some of these problems. But silicon as a material is limited primarily because it's an indirect bandgap material. And there is a class of devices, including lasers and optical amplifiers, and also different types of modulators that you cannot introduce on a pure silicon platform. Whereas there's other types of devices that use, compound semiconductors don't really scale to the same kind of demand. So what you're really looking for is some kind of technology that combines the best of both worlds. And here at OpenLight, we strongly believe that heterogeneous integration is really the way to solve some of these problems. So in terms of what heterogeneous integration actually is, this is a way basically of fabricating devices using two disparate materials in a foundry process flow. The intent here is to develop hybrid solutions using different materials without losing those economies of scale and integrating into the silicon ecosystem that has driven from the 1970s to where we are now the sort of incredible advances in computing power from there as well. So the way it works is we take wafers at our foundry partner, we pattern layers, including passive components, waveguides in both silicon and silicon nitride, and then we selectively prep areas on those wafers for bonding dies of bulk epitaxial material, primarily indium phosphide today, with different quantum well structures for different applications. In this cartoon, which is supposed to represent some kind of four-channel transceiver, you can see that there's two different types of indium phosphide material being bonded onto there as well. So the red material is for gain, that will form lasers, and the green will form modulators. But these are not devices that we're aligning on top of waveguides. We are putting down slightly larger bars, dies, chiplets of EPIs across multiple sites. And then a further step from there as well is when they actually become devices from there as well. And that is done in the foundry at wafer scale from there as well. So we're using photolithography to define waveguides, adiabatic tapers to move light between the layers and electrical contacts onto the 3,5, whilst preserving the integrity of the silicon and silicon nitride structures that we have underneath from there as well. Once those processes have been completed, the whole thing is encapsulated in a thick layer of silicon oxide, so it's passivated against the elements. And what you get out at the end is a wafer that can be tested, handled, as any other type of silicon photonic wafer can be from there. And that means we can integrate into a standard OSAT backend, which operates at scale with high volume and pretty low cost from there as well. So there's no real special handling because of the fact that you have indium phosphide devices inside from there as well. So what are the real benefits of doing this in terms of power consumption? Because we use very, very low loss couplers, typically half a dB between the indium phosphide layers, devices and the passive layers. You can reduce things like the laser power from there as well, which translates into drive current. And in fact, even just the amount of indium phosphide used is smaller. It also enables different classes of devices, including indium phosphide modulators, which we'll talk about mostly for the rest of this. And scales very nicely from there as well. So as I mentioned a couple of times, the whole point of doing silicon photonics is to get something that works at scale. This isn't just the proposition that you can make devices cheaper. Of course, that's very important as well. But you need to be able to manufacture in the numbers of the millions from there as well. And the typical way that you do this is you take optical components, you use die attach machines, you wire bond them, you put them on substrates, you attach an FAU piece by piece, which requires a lot of investment in CapEx, a lot of yield fallout throughout the process. You can only scale this basically by investing in more infrastructure from there as well. Silicon photonics actually takes a lot of this pain out from there as well. You're now creating a lot of components in a single die. You can taste it at wafer level and then dice it out, but you still have to attach the components that you cannot build. So you're not really saving as much as you might think. The real advantage of heterogeneous integration is because we're taking those die attach stages away so that 90% of the manufacturing process can be like a standard almost SMT type process from there as well. And then the last step, the you attach, is the only thing you really need to do that a typical contract manufacturer can't handle today. So it's really set up for scaling from there as well. So with that in mind, we've talked about why silicon photonics is good, but silicon photonics has limitations as well. As the industry now is rolling out 200 gigabit per lane with a variety of form factors and footprints, everything from pluggable optics through NPO down to CPO, the interest is now shifting up to 400 gigabit from there as well. And that's where silicon technologies start to struggle. Intrinsically, silicon as material does not have the bandwidth to support the greater than 100 gigahertz differential bandwidth that you need for a modulator for a good, clean, high performance 400 gigabit eye. So then we have to look at other materials from there as well. And indium phosphide is not the only material from there as well. But in terms of drive swing, bandwidth, physical size, and the fact that it is a mature system that has been used for many years, it actually ticks all the boxes. It does not have the highest bandwidth at all. I think that would either go for the thin-film lithium niobate or probably some of the excellent work that polymers and plasmonics have done from there. But both of those materials have challenges in size and integration and are not widely deployed in the sort of volumes that we're looking at to provide this AI demand from there as well. So that's really why we're interested in how you can make 3.5 modulators that work better than anything else. So this is the starting point from here as well. So here at OpenLight, we have a PDK. We've been working for many years with a number of customers. And as part of that, we've introduced into that an electro-absorption modulator. And we really like electro-absorption modulators for datacom applications for a couple of reasons. Primarily, they're small. So the device length from this, which you can see in the middle micrograph in purple, the modulator itself is only about 120 microns long from there as well. The way it works is that we take that structure in indium phosphide, we bond it on top of the silicon. There's an input coupler section as well that moves the light from the silicon waveguide into the indium phosphide waveguide, the active section from there, and then an equivalent output coupler from there as well. The output couplers are important, output couplers are important because that allows you to get the low loss from there as well. And this is basically what we have in the PDK today. It's a 30 ohm termination resistance device with about 63 gigahertz average bandwidth from there as well, measured as S21. And it can be designed into a silicon photonics flow that then can be bumped with copper pillars for full flip chip assembly and doesn't require tight temperature control like a tech for full band operation from there as well. And here I'll mention reliability from here as well, because obviously this is a process that we're rolling out and we're starting production from there as well. And I think one of the key advantages of this material system is that, we have a lot of industry experience using indium phosphide, both as a heterogeneous material or as a native material as well from there as well. So what we've done as our platform is we have qualified most of our major epitypes from there as well, according to the GR468 qual standard. That includes the gain medium, the modulator material for EAM, and indeed the photodiodes from there. And typically we run an H-toll cycle with multiple lots over multiple hours from there as well. We regard 2,000 hours as the basic stakes, and then we push devices longer from there as well. But we also do damp heat storage, temperature cycling, humidity bias, and ESD from there as well. So once you define a device with this platform, it can be handled and it will be reliable in the field from there as well. So that's great. So now we need to move from 200 gig up to 400 gig, and there's a couple of ways you can do that. As I mentioned, we like electro-absorption modulators because they're physically small, and to double the bandwidth from there as well, really you can start really by optimizing the device design from there as well. You can shrink the ridge width, you can shrink the physical length of the device from there as well. Changes to the RC time constant are really how you go from 35 to 65. And so what we've tested in the lab and the results I've showed today, we're showing better than 85 differential bandwidth from there as well, with pretty much the same structure from there as well. To go much beyond 85, and this is what we're actually testing in the lab today, you need to do a device optimization, and that's primarily a change in the indium phosphide material. As you shrink the device size from there as well, some of the other optical parameters tend to suffer. You lose a little bit on extinction ratio, for instance, from there as well. You need to maintain the insertion loss and drive swing from that as well. So by changing the quantum well structure from there is how you go from 85 gigahertz bandwidth up to 100 gigahertz, whilst maintaining the enough extinction ratio and other parameters to be able to strut a PAM4i at these beta rates from there as well. Just as an aside, one of the other things that we actually have in test as well is an OEQ circuit from here as well. This is basically effectively a high band pass filter with a low bandwidth modulator. This is another way of getting to higher bandwidths from there as well, but there is some control complexity and some additional circuitry from there as well. So what we're really shooting for is effectively a drop-in replacement of our existing EAMs, just with enhanced bandwidth to support those higher data rates. And this is kind of what we've achieved. So these are some both measured and modeled results of the device that we have in test, and was what we're sampling to customers today. And we are achieving, with the limitations of our test equipment, around 85 gigahertz bandwidth from there as well. And whilst we're limited by some of the measurement capabilities that we have today, the good thing is that it actually matches very well with the modeled results. So that gives us great confidence that our models are right, but also as we extrapolate from there, that what we're predicting is actually what we'll see in reality from there as well. And that's really sort of backed up by the fact that we can actually put data through these things and actually measure a decent 400 gigabit high from there as well. So this is something we actually had running live at OFC, if you were able to attend that trade show back in March. This is one of our EAM devices paired with an advanced driver from MACOM. That provided with a 450 millivolt peak-to-peak drive swing out of the Keysight AWG, around 2.25 volts delivered onto the EAM. And even though we're still limited by the AWG response, we're still about 20 dB below where we'd like to be in the terms of the signal path of the Nyquist frequency. We're still able to measure a pretty good extinction ratio. 4.8 is close to the 5 dB target, and a measurable TDEQ and OpenEye from there as well. So the chip you see on the device on the bottom left is a test board from there as well. It was built by TFC, uses a 3-glass via substrate with an FAU integrated in for the convenience of testing it. And you can just about see in the middle the sort of the gray block, that's the lump of silicon with our electro-absorption modulators in from that as well. So that's where we go with modulators on the EAM, but there are, of course, other modulator structures that you can do. And this is some work that was recently reported by another group using a heterogeneous integration platform, looking at Mach-Zehnder modulators. So this team produced two types of modulators from there as well. One with a coplanar strip-line waveguide design, and one with a capacitively coupled traveling wave electrode design, which is more typically of what you'd see of high-speed Mach-Lender modulators. I don't think we're reporting the length of the device from here as well, but as you can see, from the transfer functions and the S21 parameters on the bottom right-hand side, what they're achieving is actually a pretty good frequency response from there as well, and again matches very nicely with silicon. And the structure is kind of like the same of what we're talking about in the EAM. You have a silicon waveguide, you have an indium phosphide stack with a quantum well structure, and in this instance, we're just using it as a phase shifter and then combining it together from there as well. So, although we focus very much in the EAMs here at OpenLight, there are different structures that you can build from there as well, using this as a technology platform. And of course, one of the real advantages of doing this is that we're not just building modulators. So what we at OpenLight have done is we've built a PDK in conjunction with Tower Semiconductor to provide not just amplifiers, but the whole suite of components to make datacom transceivers and in fact other applications. That includes passive components, ways to get light on and off chip using either spot size converters with different mode field diameter, grating couplers for either test or production purposes, and different waveguide structures, splitters and filters, including polarization control elements, and then a suite of active components, modulators, amplifiers, both tunable and fixed lasers, DFBs for datacom, tunable lasers in both O and C band for different applications. And by using this toolkit all together, you can then create the designs that you need to. And this is not an experimental process. This is a production process, and we were very pleased to announce our first production customer earlier this year, which is a company called New Photonics, which is indeed building both 800 gig and 1.6T fully laser integrated PICs onto the PH18DA platform from there as well. And then just in terms of how you use that from there as well, obviously, we have great support from Luceda from there as well. And then we have another of our other solutions, and as I mentioned, including Cadence, Synopsys, and GDS Factory. We do supply design kits as well from this as well. We have reference designs and GDS layout cells. And customers have used most of these paths, about all of these paths now, I think, for successful tapes out from there as well. And we at OpenLight can also help with design services from there as well. So there's a wide variety of ways of using this platform. We do regard it as an open foundry model. And if you're interested in building some designs, please reach out to me or Matt or Kevin, and I'm sure we'd be very happy to help you out with that. And then finally, just an example, this is a chip that we've built and have started to sample to customers in early 3.2T prototype. So this is about a 5x7 complete transceiver design. The T-shaped structures you can see on the left-hand side are the electro-absorption modulators. There's 8 of those. Again, this ones are running at the 85 gigahertz with 40B extinction ratio that we talked about in the earlier slides. The middle section is the gain section. That includes the DFB lasers, output SOAs, and all monitor photodiodes from there as well. And on the right-hand side is an array of spot size converters out from there as well. So this is something that we're supplying for test purposes. You can think of it as a proof of concept, but also as an example of the type of circuit we can build from there as well. This is actually footprint bump matched, at least kind of identical to our 1.6T PIC from there as well. And this again highlights one of the advantages of electro-absorption modulators. Because they're physically small and because they don't change much in dimension externally as you go from one generation to the next, I'm not going to say trivial, but it's relatively easy to swap designs out between different data rates as you sort of move up the food chain. And as we're now moving away from pluggable optics, and the interest now is either on some combination of NPO and CPO, that ability to tightly integrate small arrays of modulators at different bandwidths is really one of the things we think is going to be one of the key enablers to solve some of these bandwidth challenges that we've had in the past. So I hope that's given you a sense of what we're doing from there. Just a couple of acknowledgements. I would like to acknowledge my friend Dr. Yan for the MZM data from there as well. And also, although most of what I've shown you are results that have been generated by my company, OpenLight, we couldn't have done this without Tower Semiconductor, who has done fantastic support to get to this platform to where it is today. So thank you very much to those people. And if you would like to know more, please feel free to reach out to me. I've put our info email underneath that, but there's many ways to get in touch with us. We will certainly be at ECOC in a couple of weeks now, I suppose. So I look forward to seeing some of you there. And I'll hand it back to the moderators.
Great. Thank you, Steve. That was excellent. I know for me, it's always exciting to see a PIC company that's gone to production. And I think it was your slide, product qualification status summary, that table. It's like, wow, you're like, it's not theoretical at all. This is really, really out there, making it happen. So thank you. This is great. I'll see if anybody in the audience has any questions. You can feel free to go ahead and unmute and ask your question live.
Maybe I'll start with one from me whilst people find their unmute buttons. Steve, obviously we're an EDA company, so we have slightly different perspectives, but a common complaint we hear in the PIC ecosystem is kind of the lack of reproducibility, the lack of good model data, this inability to design to spec and then tape out with real confidence. I know
Mhm.
this is something OpenLight have put a lot of focus on and one of the areas that you really excel in. Could you maybe give us slightly more details on how you convey the variability data to your customers, how you can work with them to kind of optimize for design yield?
Yeah, it's a good question. And in fact, we have slightly more challenges on that front than a traditional, silicon photonics offering because indium phosphide, quite frankly, as a material, has more variability than silicon. We see that every day from there as well. So by the time we build an element and release it into the PDK, it's not something that is theoretical. This is something that we have run multiple wafers, in conjunction with Tower. We've taken results from that. We've tweaked the designs where necessary. And then we've collected as much statistical data, both across multiple lots, across the wafer size from there as well, and over temperature. And we build that then back into the models that goes back into the EDA tools from there as well. So we provide full validation from that as well. And we showed the sort of the reliability reports, but that's really only one aspect from that as well. And that has certainly been a challenge from that as well. Anything we release into, especially the public PDK that goes out there on Tower's website, that's something that we have very high confidence in from there as well. So these are not devices that we've just chucked out into the ether. We have the management data. We know how it varies across wafer, and we have a pretty good idea of the lot-to-lot variation. And as we're reaching that point now where the number of wafers goes through Tower, we're continuing to fine-tune that and make sure that the numbers that we're publishing are accurate, but also we're able to actually start tightening some of those things up now. So that's kind of like an exciting phase for us.
Steve, maybe a follow-on on that. If I'm a company that's interested in using your process, but maybe I have some need where I need to custom design a component that isn't yet in the PDK, how would I work with you or Tower to do that? And then what kind of like does that also get similar treatment in kind of the reliability testing, or is it, am I kind of on the hook to do that myself as a customer?
It kind of depends what the starting point is. So there are building blocks within the PDK that allow you to generate both passive and active components from there as well. So the transitions, from the different layers are included in there. One of the gain blocks is an SOA that is a parameterized cell that can be used for a number of different laser architectures, for instance.
Okay.
And our PDK, we have a roadmap from that as well. As you can probably tell, for instance, things like the 400 gig, EAM is not released. And we can make that available with certain provisos from there as well and provide as much qualification data from there as well. But yes, we do custom device design, either as a deviation or a branch off the devices that we're doing, or in terms for some customers, with entirely new structures. And we're actually pretty flexible at how we work with that. We can do that as a design service, and certainly we've done that for some mostly non-datacom applications.
Mhm.
Or we can work with either partners such as yourself or with the customer directly to enable them to be able to design across both layers from there as well. But you do have to think about both layers from there. You need a certain amount of indium phosphide knowledge and experience. And again, the tool sets in terms of modeling are not as good and mature as silicon. So there are challenges. But we're happy to work with you in any form that based on the customer's need, experience, and what the starting point within the PDK is.
Great, thank you. I have more, but I would like to pause my questions and see if there's any more from the audience. I guess on that topic, Steve, if we wanted to then think about the life cycle of the chip, obviously it comes out of the fab, obviously you've done a lot of testing to make sure it's reliable and statistically, within spec. After that, if we wanted to get it packaged, like to put into a prototype or a product, do we work with you? Do you have like kind of facilitated partners that you could guide us toward, or what's the process there?
So we, as a company, kind of stop at the edge of the silicon chip from there as well. But obviously, we've been packaging these devices in various ways with a number of partners. So we partnered with, I think we've announced, with TSE in China to develop FAU technologies for this as well. We've built reference designs and EVBs and even some demonstrators, especially taking advantage of the flip chip technology. Yeah, we can work with some of our partners and help small companies, especially who can struggle with some of that. I mean, one of the advantages that we see of the platform is that it does allow you to go into an electrical OSAT system. So the company that does our copper pillar bumping, does it for everything from GPUs, down to consumer products from there as well. It's not specifically a photonic company from there as well. We use a standard dicing recipe with a pretty standard dicing machine. We test on a variety of advanced testers with probers from there as well. And all of these available at outsourced OSATs at sites globally.
Great, thank you. You mentioned datacom as a primary driver, but in kind of your later slides, you highlighted that they're being used in other applications. Could you give us a little taste of what other applications folks are evaluating your chips for?
Yeah, so we have a number of customers who are developing solutions around sort of the FMCW space, either for automotive or different sort of LiDAR type applications from there as well. And again, there are components within the PDK that work better for that. We do have a narrowband tunable laser, for instance, SOAs to boost the signal that can be arrayed up to sort of 3240 from there as well. So that's certainly an area that has its ups and downs, but certainly has applications for that as well. We have some other customers doing some areas of sort of optical or quantum compute, and even some in sort of the biomedic and sensing and consumer application space from there as well. But as you can probably tell, a lot of what we're focused on now, is driven by AI, but that's where the customization comes from there as well. So a laser that we develop for a parallel single mode application might not be applicable for a LiDAR system, but we can take that and then modify it as needed in conjunction with the customer to try and meet the needs of the system and keep the cost at about the same point.
So if I wanted to go outside O-band or C-band, maybe that could be possible if I talk to you guys and get something custom.
It is possible, yes. I mean, most of our efforts are based on indium phosphide today. Other 3.5 materials are possible. We've done some work in L-band, for instance. But yes, we're very open to looking at different material systems, for different applications.
Maybe my final question, at least for today. I see a lot of expertise in the attendees, both from from foundries, from industry partners. Are there any challenges that OpenLight are working on where they're looking for collaboration, or more generally within the PIC ecosystem that you think need to be addressed at a higher level?
So look, I mean, capacity is constrained everywhere right now. There are specific supply chain constraints on indium phosphide that I think are well known. Some of these are caused by the geopolitical situation, which may get worse, according to some news reports from there as well. And the sort of integration outside of the photonics into the electrical ecosystem, and as package sizes start to reduce down, and the need for tighter integration for things like electrical power budgets for LPO. One of the things that we're starting to get more interested in now is integration with the electrical layer, physically, as well as from a design perspective.
I guess if I read into that, maybe that's what's driving the release of your Cadence PDK, possibly.
You might think that I couldn't possibly comment.
Great. Thanks, Steve.
I think we have a question. There's a hand up.
Yes.
Yes, hello. Abanub is here. Thank you so much for sharing your work. This is amazing, and thank you so much for yeah. I am currently working in photonics design, and I have a little bit of a background in computation lithography. And I was wondering if you've shared this already about the minimum dimensions that you're working with, and whether you have customization through managing in that direction. So can you share more on this point?
Unfortunately, I can't share a lot of details around that as well. That's one of the trade secrets that our foundry processor owns from there as well. We have obviously, we're building DFB lasers, so we have the ability to create gratings with sufficient pitch to support both O and C band operation, down to around sort of like a 2 to 400 gigahertz tunnel type spacing from there as well. But I can't really comment much more about the process node, unfortunately.
Got it. Thank you so much.
Steve, if someone wanted to dig into the process side, would that be something they could go to Tower for, or would that be more of an OpenLight question, maybe under NDA or something?
Either ourselves or Tower would be very happy to answer questions about that. Yes, but obviously, it's does need to be a conversation under NDA at that point. Yes.
Certainly. Happy to take more questions. I was wondering, you mentioned, I think, obviously you've fabricated a lot of chips. If we were interested in getting some examples in hand, do you have, chips that we could get from you to evaluate before we decide to pull the trigger?
Very much so, yes. I mean, one of the things that, when we started the company, we had to prove very much that this is more than slideware. So we have a number of physical samples of both active and passive devices, and kits available for evaluation from that as well. And one of the things to highlight to the audience is that we're working with Kevin definitely on that aspect to make that available to a broader community as well. So yes, this is real technology. We have the samples to back up what we're saying, and we're very happy for people to test it.
Yeah, that's great. It's always nice if you can try before you buy.
Indeed. Yeah.
See if there are any more from the audience. All right. Well, Steve shared his contact information. You all have ours as well from the emails that have gone out. Feel free to reach out to Luceda or to OpenLight directly if you'd like to learn any more, and we'll be happy to field those. Thank you, everybody, for joining, and we will be hopefully seeing you back again next month for the next installment of Beyond Silicon Advanced Materials for Modulation. Thanks all.
Thank you.
Thanks, Steve.
Cheers.
Thank you.